functions, you get ratios.
Right. Sorry, I was thinking of the wrong thing.
And
I was trying to find the angle.
it's good to leave it as a ratio. In other words, I would rather say the sine of theta is 3 over 5 than I would 0.6. Just because what sine means is the opposite side
Over the
divided
hypotenuse.
by the hypotenuse, exactly. What's the tangent of theta?
3 over 4.
And the cosine of theta?
4 over 5.
Okay. Now if I move theta up to there, what's the sine of theta?
4 over 5.
Okay. Have you learned the other three functions yet?
Secant, cosecant, and cotangent?
Yeah.
Yeah.
Okay, let's talk about those for a minute. I'll leave that up there. If you want a nice little technique for memorizing, and Trig is all about memorization, make no mistake about it.
Okay.
You, more so than any math you have ever taken at this point. The other three trig functions are cotangent, secant, and cosecant.
Which are the inverses of sine, cosine, and tangent?
Well, they're the reciprocals.
Reciprocals, yeah.
Sure, they're not really the inverses. There's actually another thing that is the inverse, but they're reciprocals. What's the reciprocal of tangent?
Cotangent.
What's the reciprocal of cosine and sine?
The reciprocal of sine is cosecant, and the reciprocal of cosine is secant.
Okay, and obviously this holds true in the reverse also. In other words, cosecant is 1 over sine.
Right.
So we have these 6 identities that are incredibly important. You're not going to even be able to take the next step in trig unless you have these memorized. And sounds like you do. Notice that one way to memorize this is there's exactly one co in each pair. There's the co for that pair. There's the co for that pair, and there's the co for that pair. So you would never accidentally mix up sine being the reciprocal of secant because there's no co there.
Right.
All right. Two other extremely important identities. What's that? And this one. What's
Tangent of theta is opposite over adjacent.
Well,
Oh, sine over cosine.
correct, but there's another identity for it. In other words, trig is all about identities, and there are 11 identities that you just have to memorize, and that's the only way I know how to do it. Now, just one moment. Let me just make sure I don't have any emergencies here. I'm getting messages. Oh, okay. So what's cotangent theta? If tangent theta is sine theta over cosine, what's cotangent theta?
Cosine theta over sine theta.
Yeah. So in other words, you only have to remember that one.
Right.
You can always figure out the second one.
Right.
Just like you only have to remember the 3 reciprocal relationships, and you can figure out the other 3. Okay, there's 3 more things you have to memorize. And these are called the Pythagorean identities. Pythagorean identities. And because they're based on the Pythagorean triangle, the right triangle. But the most important one is sine squared of an angle plus cosine squared of that same angle is always equal to what?
Okay.
1.
Oh, 1. Okay.
Okay. And, yeah, memorize that. And the second one you have to memorize is tangent squared plus 1 equals secant squared. Okay?
Okay.
And then there's one third one, but you can figure it out. The third one is the cofunctions of the second one. Now, let's make sure that I don't confuse you here with the term cofunction. Cofunction is not the same as reciprocal.
Okay.
Okay? Cofunction of sine is cosine. In other words, the cofunction is you stick co in front of it. The cofunction of tangent is cotangent, which also happens to be the reciprocal. But then the cofunction of cotangent is cosecant. Notice that that's the cofunction of tangent, and that's the cofunction of secant. So if you can remember, the third Pythagorean identity is just the cofunctions of the second, you're down pat. And between those 11, you'll be in great shape. If you can memorize those 11 identities, you'll be halfway there.
Okay.
Now, what is cofunction? As long as we talked about it, I might be getting a little ahead of your schedule here. This might not be something you cover for a week or two. But the sine of an angle is always equal to its cofunction of 90 degrees minus that angle.
Okay.
The sine of 30 degrees is 1/2. And that's going to always be equal to the sine of 60 degrees, which is also 1/2.
Oh, okay, I get that. Yeah, because we had to memorize the sines and cosines of the most important angles, 45, 60,
Let's draw
90.
those two triangles. These are the most special two triangles in all of math.
Okay.
And it's really worth memorizing how to label these. Okay? Now, I call these the unit special triangles. I call them my unit special triangles. And they're the 30, 60, 90 and the 45, 45, 90. You've been dealing with these triangles for 3 years in geometry, algebra, and everything else.
Right.
And I call them the unit because the side opposite the smallest angle is 1. Okay? But the truth is that any 30-60 right triangle is going to be similar to that one.
Right.
So it could be 2 root 3, 4. It could be 10 root 3, 20.
Right.
It's the relationship that's important. That's what trig is all about, is the relationship between the sides. In fact, the word trigonometry means the measure or study of triangles.
Right.
Amazingly enough, it goes way beyond triangles. Trig actually also is an excellent tool for studying anything that's periodic at all, like tides, like breathing, like swinging on a rope swing. Anything that has a natural period, in other words, it just replicates over and over and over, lends itself to trig. And
Okay.
even more importantly, calculus uses trig in unbelievable ways. Who would have thought? Because calculus doesn't really have a whole lot to do with trig, but it uses the trig identities and stuff to be able to do integrals, advanced mathematics. So trig is really, really important in just unto itself in studying triangles or studying periodic behavior or in calculus. But probably you'll stay with triangles for a while. You'll get into the periodic behavior of trig, but not immediately. That's a little harder.
Right.
So, what's the cosine of 30 degrees?
The cosine of 30, square root of 3 over 2.
Correct. And notice that's true whether this is a 1 root 3 2 triangle or a 10 root 3 20 triangle.
Right, as long as you simplify it.
The ratio, yeah, it's always root 3 over 2. So
That's equal to the sine of 60, isn't it?
that's correct. Because if you looked at the sine of 60, it would be opposite over adjacent. And that's the property of cofunctions. And the same holds true, as long as I don't want to ignore the rest of that. This is also true. The tangent of theta equals the cotangent of 90 degrees minus theta. And vice versa. Cotangent of theta equals tangent of 90 degrees minus theta. And finally, the secant of theta equals the cosecant of 90 degrees minus theta. So these are cofunction properties. And notice that the cofunctions also have exactly one co in each pair. There's the co there, there's the co there, and we had sine and cosine. There's the co there. But cofunctions are not reciprocals. So I kind of hesitate to use that co as a secret for memorizing it, because it can confuse one.
Right.
You want to make sure you know the difference between reciprocal and cofunction. So
Right, they're not the same thing.
tell me what the secant of 60 degrees is.
So secant is, so that's going to be 2 over 3. Oh, no, it's not. It's going to be square root of 3 over 2.
Secant of 60, start with the angle. Now, the way I tend to do these in my mind is I tend to think of sine, cosine, and tangent as being the three primary trig functions.
Right. So
In fact, on your calculator, that may be all you have. Do you have a TI-84 or an Inspire?
Let me see. I'm not positive. I gotta check. I have where is it? I have a Texas Instruments 30XA.
Do you have, if you look at your keys, you probably only have a sine, cosine, and tangent key.
Right, and then if I second it, I have a inverse of each of those.
Okay, but inverse is different. Let's talk about that for a moment. Incidentally, the secant of 60, the way I do this is, well, I figure out what the cosine is.
The cosine, right.
And then I flip
So
it.
the cosine of 60 is 1 over 2, so it's going to be 2 over 1.
Correct.
It's going to be 2.
That's the way I tend to work with the three secondary functions. Okay, let's talk about inverse, because that's another really key part of trig. We take trig functions of angles to get ratios. We take inverse trig functions of ratios to get angles.
Okay.
And the inverse is designated by either a -1 or arc. Arc sine's the same thing. If I said arc sine, I would want to put a number in here, not an angle, to come up with the angle. Okay? This is an if and only if, meaning that if the sine of 30 degrees is 1/2, then the inverse sine of 1/2 is 30 degrees.
Okay.
Okay.
So you only use it for ratios, inverse sine.
Well, let's take this problem right here, this 3, 4, 5 triangle. It's another triangle you've been dealing with for ages, but I'll bet you don't know what theta is.
You're right.
Nobody does. Nobody cares. But if we wanted to solve for theta, we could start out by saying the sine of theta equals 3/5, right?
Right.
So, therefore, the inverse sine of 3/5 equals theta.
Which is, I just put it in my calculator.
Put it in your calculator. Put in the inverse sine of 0.6. You don't have to put it in as a ratio, but it's better if you think of it as ratios.
Right, because it's easier to figure out it.
Yeah, since we're always getting it off of triangles, it starts out as a ratio always.
And then you just do the division, which you get 0.6, and then you inverse sine is going to be 3. If you round it, it's 3.6. I mean 36.9.
Okay, I was going to say, the one thing you have to be certain of is what mode you're in.
Right.
Because you could be in radian mode, you could be in degree mode.
Yeah, no, I'm in degree mode.
If you're in degree mode, you should get something close to 37 degrees. That is 36.9.
What is GRAD?
I'm sorry, what?
What is GRAD mode?
That's radian mode.
No, I have RAD degrees, and then I have GRAD.
Oh. Huh. What would GRAD be?
I don't know.
I have no idea.
I'm going to leave it in degree mode.
I have no idea. I don't, none of my calculators, I have both an Inspire and a TI-84, but I don't know what GRAD is. Huh. No, not aware of that. But my point here is that we use inverse trig functions to find angles. Okay? In other words, if you knew you were standing right here and there was a light pole or a mountain or whatever, and you knew you were 20 feet from that light pole, and the light pole was 6 feet high, and you want to know what that angle is. In other words, very, very common problem in real life is to solve for angles. It's not to solve for the height of the pole, but it's to solve for the angle. So theta is going to be what?
So it's going to be the tangent of, I mean, it's not.
No, you're right. It's the inverse tangent.
It's the inverse tangent of 6 over 20.
Exactly. Okay? Now, there's a couple of ways we can look at this, if it ever... We can start out by just saying tangent of theta equals 6 over 20. Okay? And then we can take the inverse tangent of both sides. Just, you can do anything in an equation as long as you do it to both sides. Well, same thing with trig functions. Well, when you take the inverse tangent of the tangent, you're left with theta. And that ends up being the inverse tangent of 6 over 20.
Right.
So you would be able to solve for that angle. Now,
and apparently gradients are a thing.
Yeah, that's what I thought the G stood for, was gradient, but maybe,
It's 1/400th of a turn.
Really?
Yeah.
Wow.
It's 9/10ths of a degree, or...
How new is that calculator?
Oh, it looks really old, but I don't know.
Because I have never run across that. Oh, I see. GRAD is not G radians, it's gradient.
Right.
Oh, the gradient is a European term that means the same as slope.
Oh,
What's the slope of this line right here, this hypotenuse?
the slope of it?
Uh-huh.
Um,
Slope is what? What's the English?
rise over 1.
Okay, so what's the rise and what's the run?
6 over 20.
Exactly. So the gradient would be 6 over 20 or 3/10. I still don't know why they put a special key on your calculator for that. But
Yeah, I don't know.
in other words, I've never come across a need to use that key. Now, as long as you're dealing with angles that are multiples of 30, 45, or 60,
Yeah.
you can use those two special triangles to solve almost everything. Have you gotten into the unit circle yet? Probably not.
What?
Have you gotten into something called the unit circle?
No, I haven't.
That'll be what you do next.
Sorry, 1 second. I'll be right back.
That's all right. Go ahead.
Okay, I'm back.
All right. Before we get into the unit circle, I'm trying to go in the same order that my book goes. And
Okay.
the next part that they really cover is solving triangle problems. Let's just do one of them. Let's say you know that's a 28-degree angle. You're standing right here and you have a surveying instrument that lets you point it at the top of that flagpole, and it tells you it's 28 degrees.
Okay.
And you've marked out this distance, and that distance is 10 feet. How tall is the flag?
So, how tall is the flag? So you're looking for tangent.
Correct. And
So the
always
tangent of 20.
start your equation with the trig function on the left. In other words, we got the tangent, and let's call that y.
Tan y equals
Tangent,
f.
excuse me. Hold. You always take trig functions of angles.
Okay, so tan theta. Oh, tan 28
Equals what?
equals y over 10.
Exactly. Which means y, the height of the flagpole, equals 10 times the tangent of 28. And the tangent of 28 is just a number. Okay, I don't know what it is. I have all of the common angles memorized.
So the tangent of 28 times 10 is 5.3.
That's how tall the flag is. 5.3 feet tall. In other words, so you can solve problems like that. And there's even more clever problems that you can solve that are pretty cool. This next one is really cool. If the first wagon train that was coming across the west ran into the Rocky Mountains are over here, and they're like 100 miles away. Okay?
Okay.
Now, believe it or not, if they have a surveying instrument that will measure the angle of inclination, they can figure out not only how far they are from the mountain, but how high it is. It's pretty cool.
Right.
And I'll show you why. You draw two triangles. So the first triangle they do is that, and they measure that. Now let me draw it from the bottom. measure this angle, theta.
Okay.
Okay. And then they move some distance in. Remember, they don't know how far they are from the mountain. Turns out you can see Pikes Peak at about 100 miles away from Denver. So we know this is about 100, but they didn't. They didn't know if they were 100 miles or 10 miles or 300 miles. So they move 1 mile in. Take another reading. And that angle isn't the same as theta. We'll call that angle alpha. Okay. Now let's set up some trig functions and see if we can figure out what this distance is, which we'll call x, and what the height of the mountain is, which we'll call y. Remember, I have no idea how far I am from the mountain. I have no idea how high the mountain is. The only ability I have is to measure an angle, point it at the top of the mountain, and also be able to measure that I've moved 1 mile.
Right. So I'm going to assume that you set it up like a ratio.
In the first triangle, what's the tangent of theta equal to?
Y over x plus 1.
Just x. X is going to be the distance from the original site to the, to the bottom of the mountain. Okay?
Okay.
In the second triangle, what's tangent of theta equal to? Oh, tangent of alpha, excuse me.
Y over x minus 1?
Yes. Now, assuming we know theta, that's a number. And assuming we know alpha, that's a number. We have 2 equations and 2 variables. You can solve for both x and y. I mean, you know from algebra that as long as you have the same number of variables as you have equations, you can solve it. If I only had this equation, I wouldn't be able to get very far.
No.
Or that one. But if I have both of them, I'm going to be able to come up with x and y. So I would come up with x as 100 miles, and y would be, what, the height of Pikes Peak is about 14,000 feet, maybe? But that's pretty powerful, being able to figure out your distance from something and its height merely by this technique.
Right. That's cool.
So solving triangles is huge for trig. Solving for angles of triangles is huge. Now, so far we're only talking about right triangles, okay? In other words, if I say that's 5 and that's 2 and that's theta, then I can say that the sine of theta is 2 over 5.
Right.
If it's not a right triangle, you can't do any of that. In other words, if it's a triangle like that, then I can no longer say the sine of theta is 2 over 5. That definition, SOHCAHTOA, only applies to right triangles. However, the sine of any angle is always the same. In other words, the sine of 30 degrees is always 1/2. And the sine of 29 degrees is slightly less than 1/2, maybe 0.48 or so. So there is an application where you use trig to analyze triangles that are not right triangles.
You have to separate that triangle into 2 right triangles.
Well, you could. That's one way to do it. But there's something called the Law of Sines that says that the relationship between any angle and its opposite side is the same with any triangle.
Right. You taught me this last time, and actually this is what we went over today in class, but I already knew it because you taught it to me last time.
Oh, that's right, we did, because you gave me a triangle that could only be solved using the Law of Sines. But as long as I know that's like 28 degrees, then I can say the sine of 28 degrees divided by 2 has to equal the sine of theta divided by 5. There's only one variable there.
Right.
We're going to be able to solve for it. And we're going to have to use inverse to solve for it. In other words, we end up with sine of theta equals 5 times that number divided by 2. Then we're going to have to take the inverse sine of both sides to solve for theta. So to solve for that angle, I need the law of sines, and I need to use the inverse functions.
Okay. Yeah, actually, I think I was the only one who knew the law of sines on the test. I'm not. He didn't give us our test and like our test back yet.
That leads me to ask the question: how did they expect you to answer that other question? Did he give you another technique?
He gave the technique that I said before, separating into two.
In other words, he drew a vertical, separating it into two right triangles.
In fact, he told us he doesn't want us to use the law of sines, even though it's easy.
I thought about that afterwards. I realized that since you didn't have the law of sines and he was giving you this problem, that this must have been the way he wanted you to do it, was draw the
right. And
turn it into two right triangles.
The law of sines doesn't work on the ambiguous something?
Well, that's the hardest part. I mean, the law of sines is really, really easy. But there is one case where it's not easy, and it's called the ambiguous case of the law of sines. And there's two ways to learn about the ambiguous case. I've got one book that does it one way. I got another book that does it another. The second way is so much easier, unbelievable. Okay? Now, you want to cover that? And we've got about 25 minutes. We started at 10 after, so we got 25 minutes. Be happy to cover the law of sines with you. Okay.
Okay. That's what we went over today in class, so that makes sense to go over it.
And the ambiguous case? Okay.
Yeah.
Here's the problem. If I have a triangle that's two sides, starts like that, I know that's 50 degrees, say. There's only one triangle that can be made from this, and that's by connecting that side right there. So if I have a length of 15 and 5 and an angle of 50 degrees, it's not ambiguous. There is only one triangle that can be made.
Right.
However,
so wait, I have a question. Is the ambiguous one when it doesn't fall when the angle doesn't fall between the two sides?
Well, explaining where the ambiguous comes up is what's hard, but I'm about to try to do that. And there's an analytical way to explain it, really easy. And that's the easy way. Let's say that's 30 degrees, even though I haven't really drawn it like that. And this side is 10, and we're going to put another side right there. That's 8. Okay? Notice that if I told you that you have a triangle that has a 30-degree angle next to a side of 10, next to a side of 8, this is the triangle you would probably draw. But there is, in fact, another one that has those exact same three measurements. That side is 10. That side is 8, and that angle is still 30 degrees. In other words, with most triangles, if you give me three pieces of information, in other words, an angle and two sides, it is a specific, unique triangle. Only with this kind of a situation do you get an ambiguous case. Meaning,
and how do you tell?
How do you figure out that it's ambiguous? By attempting to use the law of sines. And here, let's do it. Okay? I'm going to try to solve this triangle right here. Well, first thing, let's even erase this. I don't know about that yet. Okay? In other words, I don't know if this situation is ambiguous. What makes it ambiguous is how big this angle is, how big that side is, and how big that side is.
Okay.
First of all, if this angle is greater than 90 degrees, you never have an ambiguous case.
Okay.
So the only time you have to worry about the ambiguous case is when this angle is less than 90 degrees.
All right.
So I start off by saying the sine of 30 divided by 8 equals the sine of theta divided by 10. Okay? Well, that's a number. We can solve for theta. Let's solve for theta. Sine of theta equals 10. Sine of 30 degrees, I know, is 1/2, all divided by 8. So the sine of theta is 5/8. With me?
Right.
What's theta?
Do you want me to do it?
Uh-huh.
Okay. Sine.
So you take the inverse sine of 5/8.
Uh, 38.7.
We'll just round everything off in the interest of simplification here. Now, in reality, theta is not just 38 degrees. It could also be the obtuse angle.
Okay.
In other words, if we look at trig as having 4 quadrants, 1, 2, 3, 4, and you'll get to this soon, the unit circle, and we say, well, the sine is positive in the first and the second quadrant. So even though your calculator only told you 38 degrees, the other angle that is supplementary to that is also an answer. And if you don't believe me, put into your calculator, what's the sine of 142? Not the inverse, but the sine of 142 degrees. 0.625, right?
Right.
So the sine of 38 degrees is the same as the sine of 142 degrees. I'm kind of surprised they're teaching you the law of sines before they teach you the unit circle. Because, the unit circle is what takes trig beyond 90 degrees. In other words, you'd not just, even though trig is the study of triangles, you can also have the sine of 150 degrees. You can also have the sine of 210 degrees. You can have the sine of 1,000 degrees.
Right.
Okay? So
We've done that. We haven't used the unit circle. We used angles that, coterminal angles to figure those out.
okay, it's not quite the same, but getting back to this problem. In other words, your calculator only gives you the principal answer, which is that one. What you have to know is that the angle that is supplementary is also an answer, which is that one. Now, the question becomes, can I fit this 142 degree angle into this triangle? Is it possible? Can I make theta 142 degrees?
Well, not in that triangle.
Yes, actually, not in this one, but if I draw the triangle like this, that angle right there is 142 degrees.
Okay.
And it fits because the sum of the angles have to be less than 180. So if this is 30 and this extra angle I figured out, add to less than 180, then you do have both possibilities. In other words, I can have one triangle that looks like that and has those same 3 dimensions, which is 30, 10, 8, or I can have the triangle that looks like this. Okay? Now,
And so that,
let's say that instead of 10 and 8, I made this number some big number. Let's make it 20. Okay?
okay.
Now, when we go through our numbers, you'll see what happens. The sine of 30 degrees is to 20, as the sine of theta is to 10. Well, now that's 1/2 over 20.
Well, we automatically know that it has to be smaller than 30 degrees.
No, it's going to end up, well, let's take it through to the limit, because that's the true test of the ambiguous case. And you're not going to understand it until you see a case that's not ambiguous. In other words, I know from looking at this thing that I can only draw it one way. There's no way that 20 is going to fit at that other angle. But what's going to happen is the law of sines is going to tell me what it is. Okay? So I've got the sine of theta equals 1/4. Tell me what theta is from your calculator.
14.5.
Which means the supplementary angle is 166. Let's round everything off. Let's make that 14. We'll make this 166. Now notice, can 166 be an angle in this triangle that already has a 30-degree angle in it?
It's pretty close.
No, it's not a question of close. It's a question of whether it's greater than 180 or less than 180.
It's less than 180.
No, it's greater. 30 plus 166 is 196.
Oh, plus.
So that means that is not possible.
Oh, okay.
And that tells me that this is not the ambiguous case.
Okay, I did the sine of 166, and it gave me basically 0.25.
Well, but yeah, what you have to do is to check to see if this angle added to the one known angle in this problem, that 30 degree hasn't changed, and it doesn't change even if it's an ambiguous case, but there's no way I can fit a 166 degree angle in there. Even if I draw it like that, that's the most you can have is 150. You can't even do that. Most you could have is 149.
Isn't it a law that the biggest angle is always, well, a bigger angle is always with a bigger side?
Yes, that is.
So we know that it's going to have to be smaller. The angle, like theta, would have to be smaller than 30.
Yeah, in terms of the ambiguous case, and believe me, this is the only thing you could. You're smart. You are not going to have any problem at all with the law of sines, except understanding this ambiguous case. And to really understand it, you don't have to even know in advance whether you have it. The book I said that is hard has a whole page of things that tell you whether you have the ambiguous case. In other words, if this angle is less than the sine of that ratio, and then 2 or 3 other rules. Okay? You don't need to memorize those rules. In other words, there's no need to know in advance whether you have the ambiguous case or not. The way to find out is to try to solve it.
Okay.
And every time you solve it, you're going to come across this step here, where you get the sine of theta equals some number. You have to figure out theta. Always make sure you figure out both angles.
Okay.
In other words, the only answer that makes sense here is that theta is 14 degrees. In other words, what this triangle really looks like is something like this, where that's 30 degrees, that's 10, and that's 20, and that's 14 degrees. But there is no second triangle that has those 3 numbers in that order.
Will the supplementary angle of a non-ambiguous case always go over 180?
Yes. Only when added to that angle.
Right.
In other words, this is the first step where you always figure out both answers.
Right.
And you see whether this is possible to have in this triangle that already has a 30-degree angle on it.
Right.
And
Okay,
the first time we did it, when it was 10 and 8, yeah, that came out to be 35 degrees or something. There's room.
Right.
There's room for that angle. And
Okay.
so you ended up with two different answers. One answer used that as one of the angles, and the other answer used that as one of the angles. But and they may or may not teach it to you like this in the class. They may do the hard method, which is making you memorize the list of rules that would tell you, without going through the law of sines, whether or not that was an ambiguous case or not. I don't even remember
This is the fast way to figure out if something is, right?
What's that?
This is the easiest way to figure out if something is an ambiguous case or not.
The only problem with this is every time you solve a triangle, you have to figure out both angles. But figuring out that second angle isn't hard. In other words, 14 degrees and whatever is supplementary to 14 degrees. Easy. So now the question is, can this angle fit? If it can't, you do not have the ambiguous case. If it can, you do. It's as simple as that.
And if you do have the ambiguous case, basically what you're doing doesn't work?
No, it works. Let me show you why it works. Remember, the law of sine does not violate the law of sines. Here's my two triangles. That's 10, that's 8, that's 30. That's 30, that's 10, that's 8. Same three things. In other words, you're going to get questions as you have angle A is 30, you have side C is 10, and you have side A is 8. Solve the triangle.
Okay.
If that was the information I was given,
you get both answers.
Well, I would come up with this answer with the first angle that I came up with, and that would be that theta right there. But then the supplementary angle to theta also works. In other words, that angle alpha is supplementary to theta. Well, why does the law of sines still works? Well, because you have, in this triangle over here, you have 10 over the sine of theta, and in this triangle over here, you have 10 over the sine of alpha, but alpha is supplementary to theta, and the sine is positive in the first two quadrants, so this is the same number as that. So there is no violation of the law of sines. The law of sines merely says that the relationship between the sine of an angle and the measurement of its opposite side is the same in a given triangle, always. So, having two possible triangles that fit this scenario is valid because the sine of 166 degrees is the same number as the sine of 14 degrees.
Okay, so when you get an ambiguous case, would you give both answers?
Yes. And this angle right here is that supplementary one. In other words, if this angle turned out to be 40, well, then this angle was 140. And notice that a 140-degree angle fits in there, which makes that angle 10, and this angle up here 110. So those are my three triangles, or two triangles, and now I can solve both of them. In other words, I've got all three angles here. Figuring out that side's easy peasy using the law of sines. And over here in this triangle, I got all three angles and two sides. Figuring out that side is easy peasy. The goal when you are solving triangles is always to solve for all three sides and all three angles. And what they always give you is three pieces of information. They may give you side, side, angle. They may give you side, angle, angle. In this case, when you're looking for ambiguous cases, what you're looking for is angle, side, side. Those are the possible ambiguous triangles, as long as the angle is less than 90. In other words, if I start out with a problem like this, and I tell you that angle is 100 degrees, and this is 10, and that's 8, no way can that be ambiguous.
Okay.
Only angles less than 90 degrees can be ambiguous triangles.
Right, because a supplementary angle to anything in that, anything else in the triangle will be over 180.
Exceed 180, yes.
Okay.
Now, there's something called the law of cosines also. Did you do that today, or is that probably tomorrow?
Do we have tomorrow or do we have Thursday?
Thursday.
Is it at 7?
Thursday is our next session. So you didn't get the law of cosines today? Let me give you a quick review of the law of cosines.
Okay.
Not really that hard. If you have those three pieces of information, side, angle, side, notice that the law of sines does not do me any good yet. I cannot begin this problem with the law of sines.
Because you don't have an opposite.
I don't have a relationship. I need at least an angle and an opposite side. And here I have an angle but no opposite side. I have two opposite sides but no angles.
Okay.
So if you cannot use the law of sines, you use the law of cosines. And the law of cosines says that A squared equals B squared plus C squared, looks a lot like the Pythagorean theorem, minus 2AB cosine of capital A. And there's actually three laws of sines because you never know which side you're solving for. So B squared is equal to A squared plus C squared minus 2AC cosine of B. And the third one is C squared equals A squared plus B squared minus 2AB cosine of C. Notice the pattern.
Right.
In other words, these two letters here are always those two letters. This angle here is always the angle that goes opposite that side. So you only need to memorize one of them.
Okay.
You can always figure out the other. And you never know which one you might need. In other words, if I have a triangle A, B, C, maybe they gave us this angle here and these two sides. Can't use the law of sines on it, but I can use the law of cosines, and I would use that one right there because that's little c. Okay, notice how it would unfold. Let's solve for c here. Not completely necessarily, but just to show you, c squared, and c being the length of that side, little c, is going to be equal to little a, which I know is 8 squared plus
10 squared
minus 2 times 8 times 10 times the cosine of that angle, which I know. Everything on the right side is knowable. There's no variables over there. So c is the square root of that number. Now, once I come up with c, let's say that comes out to be 7, I finish solving the triangle using the law of sines. You always finish using the law of sines, even if you start using the law of cosines.
Okay.
Because once I've solved for that, now I have a side and an angle. That's all I need to figure out angle A and angle B.
Okay. That makes
Okay?
sense.
There are only two situations where you use the law of cosines. One is the kind I just showed you, where you have side, angle, side, and the other is
Okay.
where you have side, side, side. And that's it.
And in that case, you would know little c.
Well, if I
Yeah.
can solve for one of these angles, I'll be home free, right?
Right.
Because once I get one of the angles, I can finish solving the triangle using the law of sines.
Right.
So I can pick any of these three and solve for the angle. Well, let's use the third one. So I'm going to be able to say 6 squared equals 7 squared plus 8 squared minus 2, 7 times 8 cosine of c. Well, notice the only variable there is that.
Right.
So I can solve for c. In other words, I'll end up with cosine of c being equal to some number. Take the inverse cosine of that number, and I'll come up with an angle. Let's make believe that that angle is 52 degrees. Okay? Well, once I get that angle, I'm home free. I'm going to use the law of sines to solve the rest of the triangle.
Right.
So the only two situations are side, angle, side, and side, 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 where you have to use the law of cosines.
Okay. See, yeah, I never thought there was a way that you could find find angles from just having sides.
Yeah. No,
Okay.
it's pretty powerful. And it also does one last thing. I know we're a little bit over, but let me just cover this. If I told you I have a triangle 5, 4, 10, is that possible?
Yes.
Actually not.
No. No.
There's another rule in triangles that says any side has to be less than the sum of the other two and greater than the difference.
Okay.
You wouldn't be able
So
to
it has
draw a
to.
triangle. The shortest distance between 2 points is right there, right? So
Right.
if 10 is the shortest distance between those 2 points, then how can I get there by going 5 in a crooked line and then 4?
Right.
So there are some
Okay. So
triangles that are
it has to be greater
impossible.
than 1, but less than 9.
Yes.
Okay.
I always start off and it's any side. In other
Is that
words, no matter what the triangle is, if I have a 6, 7, 8, okay? In other words, 6 has to be less than 7 plus 8. 6 has to be greater than 8 minus 7.
okay?
7 has to be less than 6 plus 8. 7 has to be greater than 8 minus 6. So I only remember the very first part of it, and it's reverse. In other words, I always start out with any side has to be less than the sum of the other two.
Right.
Because you can always figure out the second part of it. The second part is the opposite, meaning or greater than the difference of the other two.
Right.
Okay? Well, if somebody gave you this triangle and said solve it, and you didn't know, they gave you side, 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 and you go ahead and try applying the law of cosines in order to figure out all the angles here, you'll end up getting a cosine of c that is greater than the number 1, which is impossible.
Okay.
Sines and cosines always have to be between -1 and 1. It is impossible to have the sine of any angle be 1.1.
Okay.
So these impossible triangles you discover when you try to solve them. You end up with cosines, or in the case of the law of sines, sines that are equal to a number that is outside the possible range for sines and cosines.
Okay.
Okay?
That seems like an SAT question.
Well, we covered a lot tonight, but it was good stuff, and it's good that you're covering that in class. Like I said, you'll probably cover the law of cosines tomorrow, because that's a big part of trig is solving triangles. Not just right triangles, but solving triangle with any angles and any sides, and determining whether they are possible to have a triangle with those dimensions. And the law of sines and the law of cosines will give you answers that tell you, no, that triangle is not possible.
Okay.
All right. Next, I will let you go. Now, our session is scheduled for 4:30.
So 7:30 here?
6:30 there.
Okay.
You're 2 hours ahead.
Okay, 6:30.
Uh-huh.
All right.
See you on Thursday, or talk to you on Thursday.
All right.
All right. Bye.
All right, see you.